Great. And let me then share with you some a video made by the communication of EuroCC and Castile to just tell you about the project, who is financing anyway this event, and having you in the EuroCC and Castile projects. Okay, so let's share this. And
ranging from the areas of health and food security to energy and the environment, we are facing more and more societal but also technological challenges. High-performance computing, or HPC, in combination with HPDA and AI, provides the means to tackle not only these large, complex problems, but also to widen further use and uptake of iterative modeling and simulation technologies in academia, public administration and industry by processing massive data and performing complex calculations at high speed. But what is the value of such a toolset without the competence to utilize it best? Thus, the European High-Performance Computing Joint Undertaking addresses this field by implementing the EuroCC project as part of their funding activities. Within the EuroCC project, National Competence Centres, or NCCs, are created over a period of 2 years in 33 participating countries. These NCCs are intended to serve as a single point of contact in each European country, bringing together the national stakeholders and thus boosting the use of HPC and associated technologies. To maximally utilize synergies between all participating countries and national competence centers, the coordination and support action, Castile, is in place and active on a cross-national European level. By providing access to the excellent toolsets and enhancing European competitiveness as a whole, we can better face the challenges of our time. Visit us at www.eurocc-access.eu.
okay, so that's all about EuroCC and Castile without taking other time to our event. I leave the floor to Martina to introduce the first speech. Enjoy the event, and in case you have any need, please drop a message in the chat. Thank you.
Thank you, Luisa, and thank you all for participating today. And it's a great pleasure to me to present our first introductory presentation by Li Zong from the NCC German and Sven Carlson from the NCC Ireland. They will provide us with an extensive overview on the main challenges of artificial intelligence on HPC. And so if you are ready, Lee and Sven, I give the floor to you. You can share your own screen. And thank you.
Thank you. Give me a second.
Yes.
Can you see my screen now?
Yes, now we can see your screen.
Good. So shall I switch on my video or not?
Yes, you can.
Okay. Then I need 2 seconds more.
Yes, no problem.
Now can you see it?
Okay. Now we can see you.
Okay, good. And also the slides is?
Yes.
Okay, good. So thank you. And good morning, everyone. My name is Li Zhong. I'm currently working as a researcher at the High Performance Computing Center of Stuttgart, which is a center unit of University of Stuttgart. And together with my colleague Sven Carlsen from the Technical University of Denmark, who will give overview of the we will give a brief talk about the overview of challenges and techniques for scaling AI on HPC. And here is the agenda for today. So firstly, I will briefly introduce HRS in a nutshell. Then we introduce the background and the motivation for this talk. And then we will have introduction about the main challenges of AI on HPC, especially the challenges when we try to scale deep learning applications on HPC. Then finally, we conclude our talk with a few remarks and the outlook. So first, regarding HRS, it's a central unit of the University of Stuttgart, which started to conduct the supercomputing stuff since 1968. And HRS, in fact, is the first German national supercomputing center, which is founded in 1996 and has many services for German research at that time. But from 2004, we start to open for European users, and we are open for partners from German industry and also for HPC companies across Europe. So currently, we have a new machine which is called Hawk, and it has 26 petaflops per second of peak performance. And our main focus are about the research and engineering. So in next, I will introduce the background about AI deep learning. So we have heard a lot of times AI here, AI there, and also machine learning, deep learning, as well as big data. So what are the relationships between them is illustrated here. And in fact, in the past years, AI has shown success in various fields, such as the natural language processing, computer vision, robotics, etc. The techniques developed in AI research, in fact, stem from four main aspects, which are the cybernetics, the symbolic and the sub-symbolic, and also the static machine learning. So machine learning, in fact, is a subset of AI, and it's kind of method sets that build a mathematical model to do prediction or decisions without being explicitly programmed. And as a subset of machine learning, deep learning is often regarded as a new research area, and it uses neural networks with multiple layers, namely deep neural networks, to achieve the goal of machine learning. So, and also big data is also prompting out because it usually adopts machine learning and deep learning algorithms and models to deal with data sets that are too large or too complex to be dealt with by traditional methods. And here is brief illustration of deep neural network. As you can see, we see a deep neural network in two scales. Here is a single operator, and the composition of such operators in a layered deep network. You can see that we have painted out some common layers in a convolutional neural network, like a convolution layer, pooling layer, fully connected layer, and extraction functions. So I'm sure that most of you have already know a lot about deep neural networks, so we'll not talk much here. And as we have already seen that the deep neural network, the AI deep neural network has playing a vital role in the current industry and the research area. So why do we need to scale AI on HPC? So firstly, when we talk about AI applications, we are not talking about some toy-sized work you often see everywhere. So like handwritten digit recognition, classify dogs, cats, self-filters. So these are quite, shall I say, simplified work. But we are talking about more complicated and complex systems like autonomous driving, flying, like climate modeling and weather forecasting, like modeling of complex socio-economic aspects, like for example, we model the migration flows, and also something like a smart city. So for these complex AI applications, it often requires very large data to be stored, and also it requires a faster data exchange and thus the interconnect. And also it requires large amounts of processing power. For some applications, the response in real time are often necessary. So we think, okay, perhaps HPC could fit here. In fact, there's a saying that deep learning is HPC because training of such deep neural network requires accelerators like GPUs, FPGAs, or the new generation like graphical IPU. And training of such models also very, very compute intensive, which requires using many accelerators simultaneously. Here is an example. I'm not sure whether you know the model GPT-3 or not. It's mainly used for natural language generation and language understanding. A single GPT-3 model is composed of 175 billion weight parameters, and it requires roughly 350 gigabytes of memory for training. So if we train a single model on a single V100 car, then the time to be trained is roughly around 355 years. And if we train on a single 800 car, the time that required is roughly 90 years. So you can see that such compute-intensive computation is almost impossible or makes no sense when we do not use HPC. So we have talked about why the AI area needs HPC. Now we also want to say something about why HPC needs AI. So as HPC center, we noticed that, or we observed that customers tend to run more and more data-intensive applications, which always result in vast amounts of output data. For example, a single turbulence simulation of axial fan with just 4 rotations will result in around 80 terabytes of data, and such great amount of data makes the domain experts no longer able to analyze data manually in a timely manner. So that's why today HPC centers are in need to provide a seamless integrated data analytic and AI solutions to process data ideally on the fly. So when we're scaling AI applications on HPC, of course, it's not so easy. Model training on HPC is not a very trivial task, but to achieve the peak performance is, because of the fact that there exists several gaps between the two workflows. And we have listed here in this image, you can see. For example, the schedulers for HPC are often batch schedulers like PBS, Slurm, which evaluates the resource requirements and priorities of a job and distributes the job to a suitable compute nodes. While in deep learning training, such work are often done by VM or container management, and the deep learning schedulers often refer to how to map the deep learning training process to the processing nodes in infrastructure. And also you can see that the programming languages are different, the hardware sometimes also different. as we talked about, the programming language of deep learning and HPC are often different. For example, in deep learning, we often use high-level languages like Python, and the dependencies are always dynamically loaded during runtime. But for HPC system, we always load modules or specific HPC libraries. And for example, there are some significant challenges in building the mathematical libraries like IBM's Excel compiler, which needs for NumPy and SciPy packages that are in turn needed for the PyTorch. Similarly, while C++ interfaces are supposed to be efficient compared to their Python counterparts, we find that the current available C++ implementations are either non-existent or under development. So even in HPC systems, we have some package managers like Stack, Easy Install, which could help develop components. It's very, very difficult to get deployment with specialized compiled toolchains and the newer system architectures. So the current state-of-the-art solution is to deploy everything through container, which offers several advantages over native build. So for container, it's a self-contained software environment that is robust to software stack changes, except for the occasional driver upgrades. And its container could also offer faster deep learning application loading time, because the container is copied over to memory on compute nodes when launching jobs, and it does not just a shared file system to dynamically load the dependency libraries. And a container could also potentially enhance the productivity of a deep learning run, because both the software environment and the input-output files can be shipped in a container image, and which could definitely offer a measure of integrity for a job run. But also there's a drawback for the container, because it usually requires the rebuild of the entire software stack for tuple in the building file or upon adding a new library. For the scheduler of HPC and the deep learning, we just briefly introduced that. The traditional HPC workload managers like Slurm talk, they always lack efficiencies in container scheduling and management, and often do not provide integrated support. Sorry, do you have questions? Okay. For environment provisioning, furthermore, regarding the development of deep learning training on HPC, it usually needs to parallelize its workloads and scale to more HPC compute nodes in order to speed up the whole process. So the current state of art is to optimize the containerized AI frameworks to better suit HPC infrastructure. For example, we containerize the deep learning framework Trovare, and for massive usage of containerized application HPC clusters, container orchestrator is all widely adopted. For example, at HRS, we developed a plugin which is called the WLM operator, which is used together with Kubernetes to enable Kubernetes to schedule our containers on HPC system, because Kubernetes does not natively support HPC system, is mainly used on cloud. And also another challenge is how to distribute the model and data set, because for complicated applications, the networks are usually very, very large, and it has many layers, it has many weights, And when we do the back propagation and the gradient descent, how can we do that? How can we split it into different cores and different nodes on HPC system is quite a challenge. Another thing is that the data sets are also very, very huge. For example, in the YouTube 8M benchmark data set, it has around 8 million videos, and which is roughly 300 terabytes. So mainly we solve it with different distributed training schemes, like data parallelism, where the whole data set is split into batches and allocated to different workers, and each worker has a replica of the model, and it's here you can see. And another thing is the model parallelism, which we split the network into different parts, and each part is allocated to a worker, and during the training process, they keep synchronizing, so keep communicating among the workers, so that the communication overhead for this method is very, very huge. Another method is called pipeline parallelism, which we split the layers of the stages of the model to different workers. So now I will hand the microphone to my colleague Sven, who would like to give you more examples of the importance of HPC, machine learning, and AI. Sven?
Thank you so much, Lee. You can keep the previous slide, and I'm going to start there. So if you go back to one.
This one?
Yes, thank you so much. So it's a pleasure to be here, everyone. My name is Sven Carlson from the Technical University in Denmark, and I'm also engaging in the NCC in Denmark. So thank you so much for being here. So of course, this is a quite complex and challenging application area, as Lee has mentioned here in these brilliant slides here. One thing I like to stress here is that really we are working in an entirely new field with respect to user requirements and updates to software infrastructures. TensorFlow is not an application like or even PyTorch is not applications like we are used to in the HPC domain, where the applications are fairly static. They have some input set. You can characterize the applications, and you can get a good understanding of how you can fit the applications to infrastructure. PyTorch, TensorFlow, these infrastructures for AI are really tool sets where domain experts, data analysts, modelers, etc., are building custom tools. And these custom tools can behave radically different from each other. So in a way, working with AI, and again, this is introductory. Some of you know this all well, so apologize if this is too simplistic for some of you. I'm sure it is. You can really compare TensorFlow and PyTorch to something like MATLAB. So you can essentially do whatever you want with these frameworks. This also means that the characteristics and the behavior of your AI applications can be radically different, right? So just give you some taste of what's going on here with respect to training. So we're going to continue talking about this slide here. So when you train a deep neural network model, as Lee has been talking about so far here, then you need to iteratively run through your data sets. Again, Lee mentioned here about one data set with 300 terabytes. That's not the largest data set we have available. You need to iteratively run through all parts of this data set over and over again, and you do that through random access. So essentially, you randomly go through the data set. So let me take you through why you do this. So when you're training a deep neural network, again, as we can see on this slide, you have one part that is working on updating and training the model itself, and you have one part of your application that produces data, and this is commonly called augmentation. So you have a data pipeline that reads in data from your data set, and then you start manipulating the data. So one aspect you do, for example, if you're working with image data or video data, as you commonly do with autonomous systems, for example, then typically what you may do is to change the quality of the images, or you change the aspect ratio of the images. You may flip them, you may change color, you may artificially change exposure rate, you may rotate and distort the picture. And the reason why you do this is that you like to train a model that is resilient to small defects, right? So you don't want your car to steer off the road if, for example, encounter an unusual car color in the opposing lane. So in order to do that, you use augmentation that essentially randomize the data input. Then again, in order to train networks effectively, you can't train the network using the same data sequences. So what does that mean? So if you train the network previously with first image A and then image B, you should not train again presenting the model with images in the same sequence. So what you do is that you try to randomize a number of different aspects, not the least the way you walk through the data set. So you can think of this as actually doing fully random walks all the time through your data set. Another aspect here that is quite challenging with respect to or compared to the workloads that we may be used to in our systems is that it's not enough to go read through the data set once. You may need to go through your data set thousands of times in order to train a large network. So essentially, when you're training here, what you're going to do is that you're going to hit your I/O system constantly, and in many cases, the training workloads will hit your I/O systems in the worst possible way. It may even saturate all your available I/O bandwidth for one single application. So really, this is what we are working with here, right? So there's a new application domain. We can't really sort of think of these as huge monolithic applications that we run and plan for. Really, each day, each week, each month, there could be significant updates to both models, TensorFlow, and the actual training scripts that users use. So TensorFlow doesn't provide you with a training solution. It provides you with a number of components that you compose into a training solution. So it's really up to the model developer and the data scientist to design the training setup. So two models are not trained the same way. So again, coming back to the comparison to MATLAB. So Lee, please, if you can move to the next slide.
Yep.
Thank you so much. So another element of this that makes things challenging is that models increase in size extremely quickly. So Lee mentioned GPT-3, I hope I got that right, which was state of the art not so many months ago, but it's already outdated. So I'm sure many of you have read this famous survey by OpenAI that points to that the needed computational capacity for AI training roughly doubles every 3.4 months. This is significantly quicker than Moore's law when Moore's law was in effect, right? So really, we have a challenge here that we essentially need to double our capacity every 3 months, and of course, this is something that's extremely challenging. And here it is also important to start working very proactively with users, I believe. So I think we have over several decades worked very proactively with our users, making sure that we train our users into using the right technologies. Here, things are moving so extremely quickly that it may be the opposite, that we need to sit down with users in order for them to teach us how we can help them. So I see the chat. So should we all switch immediately, or what's going on? It's only for the.
Just go on. We will switch to another tool after the Q&A after this session. So I profit, Sven, to tell you that you have a couple of minutes to close the session and start the Q&A.
All right, thank you so much. Okay, let me know how we approach this, because I got a little bit concerned that something was off, so we need to move immediately. Sorry.
Yeah, no worries.
Okay, so I speed up a little bit to be back on time here. So as you can see, we have some significant challenges, and in many cases, we have challenges that are all mostly around I/O. Let me take you through a use case here. So this is a use case that happened, that I was involved in a prior role. So this was, I can't disclose detail, but this was in a commercial role. So I got involved into a project where there were training activities, and essentially the systems persons involved in the project were giving up on GPUs, essentially saying, GPUs are not effective. They are only working on 30%. So we need to look into solutions for our training problems. And based on my background here, I felt that this was not really a way to go. Right, that we had made an investment into GPUs, and I believe that the issue was not with the GPUs themselves. So thankfully, I had very good colleagues at this point where we could collect together a team of data scientists, computer architects, people very knowledgeable in HPC, much more than I am, to really do a cross-disciplinary task force on this. So we started looking into this. So one thing we did was to go about this from a holistic systems perspective, right? So essentially start looking into where are the bottlenecks. And we looked through the entire system, software, hardware, operations, etc. So one thing we noticed here is that we had a significant file system bottleneck. So this was a state-of-the-art I/O system that I think no one here would really raise an eyebrow saying that this was weird, we shouldn't design it this way. The problem was that it was several orders of magnitude slower than the training pipeline. It couldn't really cope with the random access patterns here, right? So it was several orders slower than the GPUs. GPUs essentially just waiting for data all the time. So what we did here is that we started employing some targeted flash burst buffers into the system, working also looking into the data sets and the models trained, make sure that we fit reasonable parts of the data set into the burst buffers, etc. And by that, then we got the I/O performance we needed. But again, this was something we had to do tailor-made for this particular model, right? But we didn't then get the effectiveness of the training up to 100%. So then we went back to the drawing board, looked at the system again, and figured out, okay, here is what's happening. So the pipeline, the data pipeline, the augmentation steps that permutate the input is not keeping up with GPUs. So essentially, the system was not balanced enough. So there were too few CPUs servicing each GPU, and then we rebalanced the system and got up to 100% GPU utilization. Next slide, please. So essentially, we went from 13% utilization of the GPUs up to 100% utilization over a large period of time. and essentially we could by that do an improvement by 8 times. But this required us really to work very proactively with the system, and we had to essentially do co-design between the application and the system. This is not a unique use case. So I've been talking to a lot of colleagues around the world, and they encounter similar situations when working with AI solutions. So I think what we see here, which is a key challenge, is that this is an entirely new application domain for many of us. And we see entirely new design trade-offs. And as probably you know, I mean, you have an image there of some ANOVA systems that are appearing around the world. There are now also vendors looking into this and sort of trying to provide different types of solutions. Some ANOVA is one of them, or many others, of course, that try to address these particular key design points, right? And then you have a system that not necessarily a HPC system and traditional sense, but something that's really good at these design trade-offs for AI. Thank you, Leah. Leave the floor back to you.
Thank you, Sven. So next, we will try to conclude our talk with a few remarks. So we discussed today why AI needs HPC, and also we discussed why HPC centers need to scale AI on HPC systems. And also we discussed about the gaps between AI and HPC, namely the environment setup, the scheduler, the data and model parallelization, and the communication and the I/O. So that's all for our talk today. Thank you. And do you have any questions?
Thank you, Lee. So there's no question at the moment in the chat. I don't know if there's someone who would like to pose a question.
Yes, can you hear me?
Yes.
Yeah, so I was thinking, what kind of system do you find easier to, let's say, tweak to perform better? Would it be some kind of classical HPC like Slurm or Torque, or more like containerized solutions like running Kubernetes with MLflow or something like that?
So then you would like to talk, or you want me to first talk about that?
I can make a first rough cut. So I think this boils down to the expectations of users. So many AI users have little or perhaps even no HPC background. And the notion about batching and the notion about having a scheduling system to schedule the jobs is something that many data scientists find cumbersome, I believe. So data scientists tend to be used to using online tools and interactive tools. So I think we need to start thinking entirely differently about how we manage the jobs themselves. So there is also, let's say, a user expectation gap in that a data scientist, I believe, tend to sort of, I want to have my job run now, and I like to have the solutions done as quickly as possible. And of course, this is different from sort of queuing a job, and then at some point I get the result and I expect it to happen within a certain time frame, whereas again, the data scientist may look at this and work with Jupyter notebooks, being online all the time, etc., etc. A little bit, I guess, similar to CAD workstations or sort of rough cut rendering workloads where you would like to have a result as quickly as possible, possibly even when you're looking at the system. Leah, I'm sure you're a lot better on this than I am, so I'm sure you have additional details to fill in here.
No, not really. So thank you for your answer, and I only have a few additional add-ons to your comments. So based on my experience, I think most HPC systems do not use like the batch scheduler alone or the container management alone. They mainly, I think, based on my experience, I think they prefer to use them jointly. So, for example, they start a job with a batch scheduler, and then they resolve some nodes, and on those nodes, they start the container management, container orchestrator, or directly a containers. So, come back to your question. I think like when you use batch scheduler or the container management orchestrator, I think there's no, it's not the performance or the speed is not the key factor that we take into consideration. We mainly think whether it's more convenient for the users.
Okay, so Hossein, I think you can start.
Oh, can I start? Okay, thank you. Thank you, Luisa and Martina. My name is Hossein. I'm a research software engineer at ENCCS, the competence center here in Sweden, Stockholm. And I'm going to talk about my take of available AI tools for HPC. So in the beginning, it's going to be a little bit elementary because I'm trying to build up the logic. So please bear with me. So yeah, so all we know that AI is not a robot, is an algorithm. And as an algorithm, it needs a large amount of data to be trained. So thanks to Internet of Things, there is no such a thing as a shortage of data. And as you can see in this figure here, from Forbes 2017, actually, there's exponential growth of data. And within this data, there are a lot of trends, consumer trends, prediction of the future of the business that needs to be analyzed and needs to be extracted. And this actually, I would say this goes hand in hand with the growth of AI and AI-driven kind of innovation. And as you can imagine, to train a large AI, PCs and laptop obviously are not sufficient. You need a lot more computational and memory resources. So this is the basics. That's why we need to have HPC in general. But how we are going to program AI? So there are plenty of, not plenty, but at least there are some options out there. So I guess we all know TensorFlow and PyTorch, but there are other options like MaxNet, Tiano, and also recently JAX by Google. So, and I call it anxiety of having many options. So because we have many options here, and working on one of these perhaps limits you to that specific option. So as you will see in next slides, when it comes to scaling up each of these, programs or frameworks, you need to be thorough in what you really wish to get. So how we are going to scale up an AI or deep learning or machine learning algorithm, my colleagues Sven and Lee actually alluded to that. So you have usually two, or a combination of these two, data parallelism or model parallelism. In data parallelism, you have rather small and medium-sized model, but your data, you want to train it faster. So you shard the data and you feed to the model. But sometimes you have a huge model that can't be fitted on one single processor, either CPU and GPU. So what you do, you cut the model and put it into two different CPUs or GPUs, which is called model parallelism. In general, when you have a model, you think about the size and then you decide about which one of these you want to go for. So, and the basics of, I would say, scaling up of an AI program, an AI, let's say, model, is based on these four famous primitives in MPI programming, as all know very well: all reduce, all gather, broadcast, and all to all. And these schematics, as we're going to talk about them soon again. So, but how in practice, how we are actually scaling up an AI program? So for CPU-based clusters, we usually use MPI. I haven't seen much of OpenMP, at least that's my experience. If other people have other experiences, I'm happy to hear from them. But when it comes to GPU, we have two different types. I mean, sorry, again, being rudimentary. We have NVIDIA, which for its GPU cluster has developed Nickel, NCCL. And as we all know that Nickel needs CUDA libraries to be functional. Once you have CUDA libraries and Nickel installed on a cluster, you can easily deploy any AI system, an AI model. And similarly, AMD also has developed RICL for ROCm GPUs. And I mean, when you want to program something, you really need to be cautious about which type of libraries you need to have. And there are, I mean, a couple of things to add to be added here. That NVIDIA actually introduces Nickel as a library for accelerating inter-GPU communication, and emphasizes that it's not a full-fledged MPI-like library. And actually, there are differences between MPI and Nickel. And but in general, these two are very similar, Nickel and actually even RICL. So to have an AI running on a GPU, you need to have these libraries installed. Once you have these libraries, then you can use frameworks that I talked before. One of the very flexible and useful framework is PyTorch. PyTorch natively actually supports distributed training. If you have Nickel and MPI available in backends, and once you have that, you can actually do both. You can do model parallelism or data parallelism with ease, and that's the reason actually that PyTorch is kind of a go-to tool for many practitioners of deep learning. I collaborated with a team in KB, and together with the KB team, we actually could use some language model within PyTorch, and we managed to actually train it on multiple GPU. And here you can see what sort of backend PyTorch supports and what sort of communication between the CPUs, which I've taken from PyTorch official website. So all in all, PyTorch natively can do that, can use, in connection with Nickel or RICL can upscale your program. The same goes with TensorFlow, with the difference that TensorFlow does not support MPI. TensorFlow is geared towards GPU. And TensorFlow has a different set of tools for upscaling an AI program. So, this table is again taken from TensorFlow website. So we have, mirrored strategy, which is a strategy where you copy, let me just go to this slide. You copy the program and parameters on each processor, and you update synchronously at each iteration or at each pass of the data. So this again, it's model parallelism, and you speed up your model, you speed up the training of your model by number of processors you have. You can also go for multi-worker mirror strategy. This is very similar to mirror strategy, with the difference that here the system is not topology aware, where here the system is topology aware. So here you need to specify a chief processor and worker processor and build the network to support the chief processor. And it's also synchronous updating. Another two other strategies for upscaling or upscaling AI using TensorFlow is central storage strategy and parameter service strategy. In these two cases, you have a server running, keeping track of parameters and workers feeding the data. And the difference between these two is that in central storage strategy, all of the parameters are updated synchronously, but in parameters server strategy, they're asynchronous. And you also need here. You also need to define the topology for the AI to be aware and to upscale the model. I mean, to communicate with the workers and upscale the model. So, well, so far I wanted just to show you that within the TensorFlow and PyTorch, you can upscale your model, but this needs bottom-up approach, meaning that when you write a program from the basics, then you can think about how you're going to scale it, and then choose your strategy and implement it in a way that suits you. But what if you have a legacy problem, meaning that you have written a program on your PC and laptop, and now you wish to scale it up on HPC? What you're going to do? Well, there are, again, a number of other options out there that you can use. Two of them that I am familiar with are Horrorwood and DeepSpeed. Well, I mean, Horrorwood, you might think it's Horrorwood, you know, but no, it's not actually. It's coming from some Russian name, Horrorwood, which is a folklore dance where people go hand in hand and dance around the circle, and that actually is what Horrorwood does. Horrorwood works based on MPI and nickel, and can upscale your program that's written on PC and laptop very well, and it's developed in Uber. Another program is DeepSpeed, developed in Microsoft, uses MPI, and can actually upscale your AI model very well. So again, there are many other programs here available that you can use, but these two I'm familiar with, and I'm actually working with Horrorwood. So all in all, I wanted just to tell you that while there are many obstacles along the way, but there are also ways to go around and find ways to upscale AI on HPC system. So thank you for your attention, and I'm happy to answer if there's any question.
Yes, there's a question in the chat. I would say you're saying thank you for your speech, and the question is how to optimize use if cluster means relationship between endpoint and nodes. How to choose them?
Sorry, let me see how to optimize if the cluster means relationship between endpoints and end nodes. How to choose them? Well, I mean, I should understand first the question better. Yes, yeah, the slide will be available. I will share it with you. But I guess it's all about the topology, if I understand Neeraj correctly. So of course, when you understand the workload and how you want to deal with the workload, then you define a cluster and define the topology around it. So let me know if that answers your question. If it doesn't, I will need more elaboration from your side.
Does seem that probably you've answered, because I don't see integrations on the question. So
Okay.
thank you, Sain. And it doesn't seem that we have other questions. Let's give something like some seconds to see if anything changes. No, so Hossein, thank you very much. If there are questions later on, yeah, there's a comment again from the question, the previous question. Yes, to optimize the cluster, use how many enables we should choose for nodes.
How many number of pools? By pools, you mean? Well, that depends really on the problem you want to solve or on your algorithm. Or, yeah. But yeah, I would say that depends.
Yeah, so eventually, if there are specific situations, probably the question should be addressed on that specific case.
Exactly. Yeah.
Yeah. Okay. So thank you, Hossein. I would
Thank you.
then ask our last speaker to jump in. So Billy Braithwaite of the Finnish NCC will talk about hyperparameter optimization. So Billy, when you're ready, the floor is yours.
Okay, I'm Billy. I'm working as a machine learning specialist at CSC, and this will be an extremely rudimentary presentation on hyperparameter search in machine learning. So if we start by defining what is machine learning, it comprises of 3 different statistical problems, namely the statistical learning theory of pattern recognition, or classification as is most commonly known, and regression. Then you have self-organization, which is basically a clustering statistical problem. And then we have reinforcement learning, which is mainly used in robotics and mostly involves using Markovian decision processes. The most common approach, or the useful way to do hyperparameter search in machine learning, is to use supervised learning approaches. So basically, there's 2 objectives in supervised learning: either to imitate the given operator of a supervisor, or then to identify the operator. Imitation of the operator is much computationally and statistically much more simpler problem, because you're just trying to learn the rules, the function mapping rules of your given labels, whilst try to uncover the operator is it's computationally much more difficult problem. And then you measure the discrepancy between the real supervisor's output and the given model's output. And what in machine learning, what is defined as a model is given by its hyperparameters, or its configuration. For example, how many numbers of a neural networks to use, what kind of activation functions, what is your margin threshold of a support vector machine, or any other optimizer what you're using for your machine learning model to do your statistical problems. So then the other aspect is model sampling. So this is mainly used when you have limited amount of data. So you can use either bootstrapping or cross-validation, try to get a balance between the bias variance dilemma, what is known in statistics. So you set a range of hyperparameters, and each hyperparameter defines a single model. So if you have 100 layers in a neural network, this will be a different model than if you have 101 layers in a neural network. Then, depending on what loss function you're using, and either you're minimizing or maximizing, you'll try to find the suitable model for your problem. There's basically 3 approaches to do hyperparameter searches. And 2 of these are, for example, grid search and random search. In grid search, you exhaustively enumerately search each and every hyperparameter combination what you have set. And then with random search, you give up some possible range of your hyperparameters to do random sampling from the search space to find your suitable model. These are embarrassingly parallel processing approaches, because you can evaluate each model independently from each other. But these are mainly useful for if you have a small and limited number of hyperparameters or their scopes. And especially with grid search, it is extremely useful for just evaluating for categorical hyperparameters, for example, to measure between stochastic gradient descent or atom optimizer for some model to do the search in your problem. Then the downfall of the two previous approaches that they do not take account of previously evaluated models. So here's then the third approach, which is called adaptive or Bayesian search. So basically, each model has a set of prior distributions set by the hyperparameters, and you do each model evaluation. And using the previous model evaluations, you adjust your hyperparameters to continue the search to find the best suited model for your problem. This is from a parallelizable consideration. This is a very difficult approach because this is sequential in nature. You can parallelize the actual model itself, but doing a parallel hyperparameter search with adaptive search it's difficult, but there are approaches how to do this in parallel. For example, you can partition the hyperparameter space into separate blocks, and you can use, for example, MPI primitives to do these searches. And then one of the state-of-the-art, for example, large-scale hyperparameter search is use what is known as multi-fidelity search. And one of the state-of-the-art approaches is so-called asynchronous successive halting approach. The basic idea is that you allocate a certain number of resources, and with resources it means that, for example, number of epochs in a neural network training, or a number of training samples, number of hidden layers, and so on. Then the highest ranked configuration from these resources are promoted to the next evaluation iteration. Basically, here you don't need to wait for certain configuration computations, but you can, which workers are free, you can then distribute these configurations for evaluation. And if there isn't any suitable configurations to evaluate, then you can just, this approach randomly generates from the pool of resources to get some new candidates. And there's a reference for this approach, or if you are interested in taking a look. Now, there are some problems with model selection in machine learning. For example, if you're defining too many models to evaluate, it has shown that this can lead to overfitting, which is not something what you would really want. Then basically comparing models just using a loss function is not really that helpful, because you have to do some statistical analysis on the statistical power of your model. And you can use, for example, Bayesian analysis to do this, because you're evaluating models on the same data set. You cannot really use, for example, p values or t values, because this will violate the independent clause. And then when you're doing statistical analysis of your data, there's a important question of what is the optimality of your problem, because you cannot really define on many problems. And yeah, just like said previously, you can partition the search space, maybe focus on more efficient evaluation of the model itself, doing a efficient parallel programming of it. And of course, then there are some programming language constraints also to consider. And that's about it.
Thank you, Billy. Any question to our speaker? In the meanwhile, there's a question eventually for Hossein from the previous page from Ere Inang. So there's this for multi-node with multi-GPU trainings, which backend should one choose? That's the question. So we're waiting for others on the last speech. Hossein, if you want to comment on this.
Well, I'm guessing what Niraj wants to know is that when you request for kind of a number of nodes, a pool of nodes, sometimes it shows out of the range. So perhaps, well, the command is not correct, but still I'm not getting what he's trying to tell me. So perhaps it's easier if he emails me or chats with me directly, so I can, do a back and forth and, get to the bottom of his question.
Yeah, okay. In case you can also use the email address of Castile Word Package 2, and we can, forward put you in contact at least.
Sure.
Thank you, Hossein. And going, Billy, to another question. Do you know of any approaches of combining ASHA with Bayesian optimization?
ASHA is the approach to do parallel Bayesian optimization, because you can allocate different resources for different function evaluations, and you just, for each iteration, then it is those functions which are evaluated, then those are promoted to the next iteration. So this actually is more like just a schedule for distributing the work. So you can use ASHA for Bayesian optimization if this answers your problem. Because ASHA is not itself a hyperparameter search strategy. It's more of an approach how to do the Bayesian optimization in parallel.
Thank you, Billy. I guess this answers the question. There's other points, other questions you would like to pose to our speakers? So if not, I thank you all very much for your participation, and the recordings and the presentations will be available in the EuroCC Access. Anyway, we'll email you when this is the case. And thank you to our speakers. Hopefully we will have other events like this, hopefully without technical problems, and enjoy your Friday and your weekend. Thank you very much to all of you.